Hi everybody, thanks for taking the time to join our webinar series. My name's Anya Fisher and I'm part of the Central Southern branch. Usually every year we have a seminar series day, you know, in a hotel and stuff. Obviously that's been prevented this year, so that usually happens in June. So we've actually managed to get some talks organised over the course of this week, and our theme is Coast in a Changing Climate. So I should warn you, it's obviously everyone signed up for the whole series. Unfortunately, we've had to cancel Friday's talk, so we will be rearranging that. So actually this week there's only the 2 talks, but we will definitely get that one rearranged. So just a few sort of technical things. In the chat box, our SciWem lead, Barbara, has put some links and some instructions, but basically we're going to try and, Mike's going to do his presentation, and then we're going to have Q&As at the end. So if you have a question throughout, feel free to pop it in the box and we will deal with that, answer those at the end. If you have any technical issues and can't hear or whatever, possibly best put that in the chat so we can see and see if numerous other people are having the same issue. So the few things that are in this chat box at the moment, just to publicise, there is the SciWem Flooding Coast webinar series. Again, there's one next month. There should be a link to that in there as well. But that's usually an actual seminar, like, you know, day event. But it's divided up now into some different events. But they're open for at the moment for signing up to. And there's a few more bursary things to sign up for. So there's the Margaret's bursary for early career professionals for urban drainage design for up to £3,000 for if you're working on a relevant project. So that closes on the 23rd of October. There's also Young Environmentalist of the Year. Applications for that close on the 30th of October. And there's also the UK Junior Water Prize, and that applications are open for that up until February. So feel free to take a look at those links and upcoming events. I should also note that this is being recorded and should be available on the SciWem website after this. You should all be automatically muted, so there's no issues there. But like I say, any other queries, pop it in the chat box and questions in the Q&A. And with that, I'll pass over to Mike to start his presentation.
Thanks, Anya. So I will be talking today about a project that we're working on for the Environment Agency managed Flood and Coastal Risk Research and Development Programme. My EA project manager is Lee Swift, and this is part of their ongoing efforts to make our coastal management more robust against the effects of climate change. So today it's about cliffs and sea level rise, and I've been working on this kind of problem for over 20 years now, half of that time as an academic and half of that time as a consultant. I should share some of my credentials on this really. So I've have been cited by the IPCC in their 4th and 5th assessment reports. I collaborate on this topic internationally. Was a member of the International Association of Hydraulic Research's Climate Change Working Group, their coastal member, and I'm currently a member of the UKCP18 non-governmental user group. So I've got some experience of this subject and some opinions on it. So this is the title of the project, Cliff and Shore Sensitivity to Accelerated Sea Level Rise, Stage 2. The first stage was led by Royal Haskoni DHV with WSP as a subcontractor. This second stage is being done by WSP, and we've got some help from the British Geological Survey, who are trialling the method that we've developed. The Channel Coastal Observatory will be helping to host the results. The University of Sheffield provided some really valuable sea level data, historic sea level data, and our work is being driven by the UKCP18 Sea Level Projections. So that's been crucial to our work. So the first question is, why do we need really to predict coastal cliff erosion? Well, we've got lots of assets at the coasts. people live there, there's tourism infrastructure, there's more substantial infrastructure. So bottom right here is a picture of the Bacton gas terminal. In the top left, we've got the country's low-level nuclear waste repository. And it's, so all of these are at the coast, but behind soft eroding cliffs. Some of these cliffs are defended and some of them aren't. If they're not defended, then you need to know how long you've got before the cliff reaches your asset. If they are defended, well, you need, in order to understand how much investment to put into the maintenance of that defense, you still need to know how fast the coast would retreat if it wasn't there. So you still need to know. So for all of these kinds of assets, you need to know where the cliff will be or might be in the future. And we must expect the future to be different to the past. We must expect cliff recession to increase because we know that sea level rise drives coastal cliff recession. And we know that sea level rise is accelerating and will continue to accelerate for a long time to come, hundreds of years. So the best information we've got on this tends to come from the UKCP, United Kingdom Climate Projections work. UKCP18 is the, I should say actually somebody's typing away in the background. I think maybe if somebody could mute, that might be good. Anyway, so that kind of model-based projections are really helpful in understanding what kind of sea level rise we might have in the future, and UKCP18 tells us that it might be up to 1 meter by the end of this century. There are other types of ways of thinking about this problem, including expert elicitation, which are in some ways better at exploring the extremes and give us reason to be even more alarmed by the potential scale of sea level rise. And yes, and so these changes will drive cliffs back, but there's quite a lot of uncertainty about just how sensitive these cliffs will be, whether they'll respond very quickly or very gradually to these increases. Now, as I moved from working on this problem as an academic to working in practice, I was a bit disappointed by how little resource was typically put to dealing with this problem in coastal hazard studies, coastal risk studies. So it was generally the case that you couldn't afford to use the best methods, the most capable methods to tackle this problem. And so typically one has to look to guidance documents for methods which you can roll out and apply really quickly, that maybe only take a matter of hours to apply. And there are various guidance documents that we can look to for this kind of guidance. There's here the Syria Beach Management Manual, the Soft Cliffs Handbook. The third one on the screen there, that's the method that was developed for the National Coastal Erosion Risk Maps, which of course had to tackle this problem. And the fourth one there is the Cohesive Foreshores guidebook. And these provide methods you can apply pretty quickly. I've listed them on the screen here. I've highlighted the Bruun methods here because basically to make the point that the Bruun-based methods or modifications of the Bruun Rule tend to be most highly regarded and most strongly kind of recommended by these guidance documents. Others have also been recommended or suggested. Due to shortages of time, I won't go into all of those, but I will look at the Bruun Rule because for two reasons, partly because it's the most widely recommended method and so most likely to be used, and partly to see what it says, what kind of thinking it reflects, so how it conceptualizes cliff recession, so that I can then start to question that. And I'm also going to highlight it as basically as representing the standard which, I want to offer something new to go alongside these methods. So by looking at the modified Bruun Rule, that gives you a sense of the threshold that needs to be crossed in order to provide something that's genuinely valuable. So the basic Bruun Rule, a lot of you will be familiar with this. It describes the way a beach profile might respond to sea level rise. So the solid horizontal line is an initial sea level. The solid curving line is the initial beach profile. And the idea is that sea level rises up to the dash line, and the profile shape is conserved as that water rises. So relative to the rising sea level, the profile shape is conserved. Now, in order for that to happen, the profile has to move inland a little bit. And in doing so, it releases some sediment, and that sediment is then assumed to collect lower down the profile. So the profile shape is conserved there, and with a bit of geometry, you can work out some recession distance R, which is a consequence then of that rising sea level. So in 1991, Dean provided a modified version of this. So this is the modified Bruun Rule. That's the equation. I'll just pick out a few things about it. So the R terms there, that's the recession. So R2 would be our future recession, R1 our past recession. The S terms are our historic and future rates of sea level rise. And then we've got that little collection of terms on the right, L star over P, B plus H star. So those terms there describe both geometry, so the length of the profile involved, its height essentially. They describe the cliff height, that's B. And there's also a term P there, which is the proportion of sediments in the cliff and the shore platform that once eroded would fall into the beach and stay there and help to build that beach. This is basically a sediment budget method. It's all about finding the balance in the sediment that as the shore retreats, as the cliff erodes, sediment is released into the system, and it's about finding a balance between the rate of retreat and the rate of sediment supply. You'll notice perhaps that there's no reference to geological strength in this. So if we think that this side of the equation, the right-hand side of the equation, after the first plus sign, that basically represents the increase in cliff recession due to the sea level rise. Well, if you have, say, two cliffs, one made of soft clay, one made of hard slate, if they happen to have the same profile length, the same height of profile, the same proportion of sediment that would remain in the beach, the same cliff height, then you'd get precisely the same increase in recession due to sea level rise for the clay cliff as you would for the slate cliff. And that might be a really quite modest increase for the clay, but an absolutely, proportionally speaking, a massive increase for the hard slate cliff. So this method, which is the standard, really doesn't deal with geological strength in that sense. So it's a sediment budget method. So let's ask ourselves a question: does cliff recession? So does a sediment budget govern cliff recession? And I think it's true to say that at some sites it does. So these are the cliffs at Dunwich. I was there a couple of weeks ago and took these photographs. We can see the cliff is strongly vegetated. There's not much recession going on there. Even the beach is vegetated, and that's because the beach is very full. It's quite hard for the tide and the waves to get to the cliff to drive erosion. So you can really accept, really, at a place like this, that there's this interesting dynamic balance between, well, if before the cliff recession can happen, the beach has to be denuded a bit, that has to be lowered, then the waves can arrive at the cliff and drive it back. But as it's driving it back, it will release sediment into the beach, which will boost the beach and then introduce this sort of negative feedback that will regulate the recession of the cliff. So you can sort of buy this idea that's represented by the modified Bruun Rule as being potentially, as being useful in this sort of setting. But in other kinds of setting, it seems far less plausible. So here we have a couple of sites. The bottom left is the Naze Peninsula in Essex. The top right is in the Vale of Glamorgan. So there is a beach at both of these places, but the beach is very small and it's right up at the cliff toe. And it's quite hard to buy the idea that the recession of these sites is governed by the release of sediment, but governed by sediment, the local sediment budget. It seems much more plausible, really, that it's the shore platform, the relationship between the shore platform and the cliff, which is really crucial in regulating its retreat. So you can imagine if there happens to be a combination of storms that drives the cliff back quite quickly in either of these places or anywhere like them, well, then that's going to create more shore platform, because it's been freshly created, it'll be at quite a high level. And that's going to have the effect of increasing the amount of wave dissipation that happens before those waves arrive at the cliff, which introduces a negative feedback. It makes it ever more difficult for those waves to cut the cliff back. And conversely, if there happened to be a sequence of events which cause the platform to drop more rapidly without the cliff going back, well, then overall, there's less wave energy dissipation going on. And it becomes more likely that the next event will find it that much easier to cut the cliff back. And so you can picture a dynamic balance between the cliff retreat and the platform slope. And that seems quite important for these areas. And if you look at the modified Bruun Rule, and basically we can see that it doesn't pick up that dependence for many sites on the platform slope. As I've said, it doesn't deal well with variations in geology. I mean, the historic recession rate is used, which you might think was a proxy for the rock strength, but really it's a proxy for the net sediment budget. There's an assumption in the Bruun Rule that the response to this change in sea level is instantaneous, that as soon as the sea level has risen a bit, the system responds fully straight away, which again doesn't seem to be really the case for sites like this. Once the sea rises a bit, it's going to take some time for waves to carve out a new profile shape for the system to respond. You know, it's not so easy to move rock as it is to move sand. There's going to be some delay there. Another aspect is that the modified Bruun Rule doesn't cope with growth in wave conditions, which one might have. We have some reasons to be suspicious that waves will increase in the future. So it would be better if we were able to account for that. Also, the sea level rise is treated in the modified Bruun Rule as being something that's just constant through time. And we've got good reason to believe that actually, because so the shore platform, of course, extends down into the water. It represents many thousands of years of development, and sea level rates of sea level change have varied across those thousands of years. And so there seems some reason to expect that those varying rates of change will be reflected in the form of the profile, and therefore in sensitivity to future recession. But of course, one respect where the modified Bruun Rule is good, of course, is that it picks up the sediment budget. Now there are numerical models out there which can do a better job at this sort of thing. One of them is the modeling tool Soft Cliff and Platform Erosion, which is freely available from GitHub, something that I developed with colleagues at the University of Bristol. And this ticks all of those boxes, all of those things that I've just been describing. You can see an example output on the screen here. We've got, if you look at the thick black line in the middle of the graph, picture that. So at the top of that thick black line is 0y, so 0 years. That's basically the shore profile now, as it were. We can see that's a profile in rock. We can see a yellow lens, that's a beach. And then we can see a series of profiles progressing towards the left after 100 years, 200 years, 290 years. And we can see mean sea level rising through time as this little blue dot. So each profile has got a little blue dot, and that represents mean sea level at that time. And we can see as time progresses and the sea rises, we've got a changing profile shape, both in terms of the rock and in fact the beach changes shape as well. This gives you a sense of the sort of output that SCAPE produces. We can use it to capture sediment budgets as well. But of course, the issue is that many people would regard this as being a rather time-consuming tool, even though it's freely available. It's not quick to apply in the way that the modified Bruun Rule is. So it doesn't tick that box. So that's where this research comes in, this research project. The idea of it is to construct a very large number of SCAPE models, which represent the whole of the coast of England and Wales. We've chosen 82 regions, which you can see in this image. And the idea is that for every one of these regions, we run 20 hindcasts, each of 10,000 years. So we have 20 alternate simulations of 10,000 years of formation of the coastal profile up to the present day. And then for each of these regions, we explore how it would develop under 9 alternative sea level rise trajectories provided by UKCP18. So that captures low emission scenario to high emission scenario and different percentiles within each emission scenario. We have 9 in total. So for each of those, we used to drive 100 forecasts, each of 510 years for every one of these areas. And that results in a large number of years of coastal simulation. Now we need to drive these models with time series inputs. So a time series of sea level rise, we're going back 10,000 years. So we need, that's on the left-hand side, history of sea level change. So we need to describe sea level changes over a very long period of time. And I quite like the picture on the left there. You can see it shows quite nicely the tilting of Great Britain, where we have land rising in the north, at the very north of England, and falling in the southeast. So that's isostatic rebound due to the loss of the last glacial ice sheet. We need to drive in time series of the wave climate. So this is a sort of a snapshot of wave severity around the country. You can see areas down in the southwest, the Isles of Scilly, around Cornwall, particularly large waves, Pembrokeshire, and then areas of small waves as well, in the Wash, for example, and Thames Estuary. And we need to put in time series of tides as well, and we can see that we've got a nice variation on the right-hand side of tidal conditions around the country. So it makes Britain a really interesting place, actually, to look into this kind of question, because we have so much variability. Now, we had to, in order to do this kind of broad brush modelling, we need to make some significant compromises. So we're treating the coast in 2 dimensions. We're treating the geology as invariant across the shore. I'll say a bit more about geology at the end of this. There's been no attempt to calibrate locally, so we're trying to pick up the regional effects of history of sea level change, wave conditions, tide conditions, without attempting to calibrate to local conditions. We've got a broad brush description of wave growth. We've assumed a linear growth in wave conditions up to 20% by the end of the century. Of course, producing a 10,000 year plus time series of wave conditions is, you need to make some pretty bold assumptions, do that sort of thing. And importantly, we haven't put a beach in. So that was to make the problem tractable, to avoid having just an unmanageable number of simulations. And I think the result of that is that and some other other decisions we've made, is that we've intentionally introduced a bias towards conservatism, so that the absence of the beach means that we would expect our results to rather overestimate than underestimate. So a few more comments on uncertainty. Some we've represented explicitly, for example, uncertainty in future sea level rise through the use of the scenarios. Some we've dealt with through conservatism. So where we haven't understood, for example, or we don't know for certain what sea levels were like back in the Holocene 10,000 years ago, we've made some conservative assumptions about that, informed but still conservative. And so, as I say, the results are more likely to overestimate than to underestimate, and it isn't actually possible to know how much the results deviate from the true answer. All we can say is that as investment is made to refine our understanding, so those uncertainties can be reduced. So let's look at some example results. This is one of our hindcasts. So it starts, so we're looking at a rock profile being carved by a rising sea, by waves, I should say, on a rising sea. We can see they start 10,000 years ago, that vertical line on the left. It's labeled minus 8,010, a very precise number. So that's a sort of minus 8,000 years to the present calendar, basically, so 10,000 years ago. So you can see that during the hindcast, the sea rises quite rapidly to begin with, and then the rate of rise at this location tails off. And you can see a series of shore profiles there. Each of those are at 500-year time steps. And so we can see that initially the distance between those profiles is quite big. It's indicating high recession. And then as the rate of sea level rise tails off, so the recession rate diminishes. And we can see as well that as that happens, the profile becomes more gently sloping. So you can see that we're picking up a relationship between rate of sea level rise, cliff recession. So the cliff recession is essentially the recession of the top of those profiles, and the slope of the platform. I've intentionally removed the horizontal scale because as yet the agency has to go through procedures before it can approve the release of the results. So I've taken the horizontal scale off, but you get the idea. And here's an example forecast. So a little bit more detail here, starting at 1800 and going to 2100. We've actually run the simulations to 2300, but we may not make that whole time series of results available. We might stop at 2150, say. So we can see, yeah, so these start at 1800. You can see in the 19th century, there's a little bit of sea level rise, particularly at the end of that century, but basically not very much. And the recession rate is quite low because the profiles are quite close together. So sea level rise increases during the 20th century, and those profiles get a little bit wider apart. But then when we get into the 21st century, of course, the sea level rises much more rapidly and those profiles get much more widely spaced. And what we're trying to, so we've got lots and lots of these results, you know, for every one of 82 regions under 9 different scenarios of sea level rise, and there are 100 simulations for each of those 9. So we need to boil these results down into something that's useful and meaningful. So what we've tried to capture is a measure of sensitivity. And that's quite just simply the ratio of future cliff retreat divided by past cliff retreat. So the idea is that we try to pick up some sense of this acceleration, that this widening of the profiles as we go through time. So first of all, the past cliff retreat, well, obviously we'll need to pick some baseline. And we've chosen the last 100 years, 1920 to 2020. It's a period over which there's usually good mapping data, aerial photography. So it's, you'd expect in most studies to be able to get a pretty good handle on retreat over the last 100 years. And then our future retreat, of course, would be the kind of the measurement, the horizontal distance, as it were, to each of the profiles. So you can imagine for each of those profiles under the green lines, we could work out a number, an index, or an indicator of sensitivity, which would simply be the ratio of each green arrow to the blue arrow. So that number would start below 1, would then rise to about 1, and then as it does for the result for 2060, and then go above 1. And so we're calling these conservative indicators of cliff toe sensitivity to sea level rise. It's a long title, but we want to make the point that the results are conservative and they indicate the way the cliff toe, the sensitivity of the cliff toe to sea level rise, accounting for the local conditions of tide and history of sea level change and wave climate. That's the idea. And so here's a nice map of these indicators for the year 2120 under a particular, I actually can't remember which, but under a particular projection of sea level rise, probably one of the higher ones. Now, I've not included the scale because, as I say, the agency hasn't yet approved the results for release. But we can see some interesting general trends here. So red indicates greater sensitivity, the yellow tones indicate lower sensitivity. So we can see there's this north-south split, which is quite similar to the divide that we saw in historic sea levels, basically where you have higher relative historic sea levels, you tend to get higher sensitivity. That's come out as a work. We can also find dependence on tidal range. So we tend to get lower sensitivity where we've got high tidal range and higher sensitivity where we have lower tidal range. So that's interesting. And we also get a relationship, a dependence on wave energy. so that the height and the period of the waves. Where we have relatively energetic waves, that tends to suppress sensitivity so that the sensitivity of a cliff to respond to sea level rise, it tends to suppress it. Where we've got more sheltered areas, the sensitivity tends to be amplified a bit. But of course, with all the variation around the coast, part of the value of the work is that it accounts for all of these things and accounts for the relative importance of all of those things in the output. But what I hear some of you thinking, what about the grey areas in the north? So these are regions that we simulated, but for which we're not giving any results. Well, we had a challenge there, which was caused by our representation of Holocene sea levels. So here we're looking at relative sea levels over the past 8,000 years. As the blue line, the horizontal black line represents present day sea levels. So you can see we've got the sea level rising rapidly up to 7,000 years ago, remaining static until about 6,000 years ago, and then slowly declining. And that high stand was 5 meters above present day levels. So this representation was chosen as a conservative interpretation of what sea levels might have been. In fact, it turned out to be overly conservative because our models in that area, they responded to this change in sea level. But what tended to happen at the end of the simulation, because the sea level fell so much, the cliff became abandoned. So the wave breaking, the erosion was happening just on the shore platform, and there was essentially zero cliff retreat. And we know from looking at the northeast and the northwest that that's not realistic. So it's not. These aren't regions of abandoned shore, abandoned cliffs, relic cliffs. And so we've got good physical reasons for saying, well, this data which we got from glacial isostatic adjustment modeling, it's overly conservative. And so I'm hoping that we'll be able to rerun those results with a less conservative sea level rise and so generate results in those areas. But at the moment we don't have them. So I'll now quickly show you how these results can be used to project cliff retreat, not just to give these kind of broad scale pictures. So let's look at a real site, the Blue Anchor Bay in Somerset, the southern side of the Bristol Channel. It's got relatively soft Mercia mudstone, retreating at just over 1/4 meter per year on average. There is a beach. There's a gravel and cobble. There's also a bit of an ephemeral sand beach, but that doesn't seem to be playing much of a role in regulating what's going on there. And so let's set ourselves a challenge. So to conservatively estimate cliff retreat under the highest sea level rise scenario for those 3 decades, 2050s, 2070s, and 2100s, using the results of this work. Well, so we'll have a quick look. This is the highest sea level rise projection. You can see, so that's the blue line. This is relative to levels in 2020. You can see it accelerating, curving up quite strongly. The black dashed line is continuation of historic rates. So you can see that there's a big increase under this scenario by 2120. So I suppose there's a question, will cliff response be as extreme as the increase in sea levels? So the first thing we do is to look at the map of our results, and we can see that this site is in region 55 of our simulation set. So we can go to the spreadsheet where the results for region 55 are recorded. We can go to the tab where the results for this particular climate change scenario, this RCP 8.5, which is the high climate change scenario. We can go to the tab where that's recorded, and then we get this table, and we can see that we have results for different percentiles of that climate change scenario, and we're looking at the 95th percentile, which is the highest. And then we can look up, so each row here represents a different decade, and so we can look up results for the 2050s, the 2070s, and the 2120s. which are those three numbers highlighted in green. So we can capture those. Obviously, this is a matter of a few minutes just to pull these out. And we can drop them into a table. So there, I've put them into column D and shaded them in green. And so in this table, we have in the first column the year that we're interested in. Those are the 3 years that I mentioned. We need the historic recession rate over the last 100 years. And we know that that's 0.26 meters per year. So we then need to calculate our baseline recession distance between 1920 and 2020, which you'll recall was our baseline period for this work. So that's a simple calculation, 26 meters, 100 times 0.26. Then we have our, as I say, our indicators of cliff toe sensitivity in green. And then to get our conservatively estimated recession distance that accounts for the sea level change, we just need to multiply columns C and D, and we get these results: 16 meters, 29, and 74 meters. So it really is as simple as that to apply this stuff at its most basic level. I mean, but what I hear you asking about variation in geology along the shore, well, at the end of the blue anchor frontage, we have this beautiful near vertical fault, and the geology gets harder as we go off to the left into that grey rock. So in principle, all we need to do is replace the 0.26 in that table that we were just looking at with a new number, a lower number because the rock gets harder, an appropriate historic recession rate. And then the spreadsheet, of course, updates itself, and you get revised projections of where the cliff will be. And this, of course, if you have the resources, you can collect quite a lot of data on historic recession rate. So this represents a strip of coast with 4 different cliff units in it. We put a load of transects through this coast and took a lot of measurements of recession distance. And I've coloured them by each of the cliff units. So the blue anchor one that we were looking at, those are the red circles on the left-hand side. We can see each unit has got a different average recession rate and a different upper and lower limits in it for its statistics. And we can capture those averages and those limits, and we can use them to produce alternative sort of average and upper and lower limit projections of where the cliff will be in the future. So on the left, we've got the blue anchor frontage. So now we've got lines on maps representing the forward projection of those historic rates, having accounted for the effect of sea level rise. Then you can see on the right-hand side, as you go into the next unit, the Warren Farm, well, the average recession in each case drops rather. So the green lines, the red lines, the cyan lines approach the cliff top. Because the average recession rate is less, but the uncertainty bands get wider because there's that much more scatter in the historic data on cliff recession. So you can play these kind of, well, you can make use of fairly rich data in this method. I'll skip over this bit, shortage of time, but essentially one can see how these sorts of projections can be used to start making planning decisions about whether it's sensible to allow new houses to be built, for example, within these zones of hazard. Okay, so I've been trying to explain that it's a simple method to apply, and it gives us new insight. I have to highlight and really stress the limitations, of course. So this is based on broad scale modeling, idealized conceptions, simplified representations of the conditions. There's no beach. The coast is treated in 2 dimensions. We haven't calibrated to local conditions. We assume that the geology is the same across the shore. And we've made this very simple assumption of 20% of growth in waves. The work really provides regional insights rather than local detail, although you can work in some local detail that you've observed as you're applying the work. It captures the importance of historic sea level change, tidal range, and wave climate. It doesn't deal, of course, with other influences on recession, landsliding, alongshore influences, coastal catch-up, and coast protection. And in each case, bespoke modelling should provide better results, and this is really to be recommended greater detail, better results will be got if you take the time to construct a bespoke numerical model. And if you consider SCAPE to be appropriate for your site, then that's freely available for you to use. And then finally, SCAPE itself, of course, is imperfect. There are relatively few models which can do this sort of thing. And so it would be great if there could be more investment to improve SCAPE or to develop more models which also capture the dynamic reshaping of the shore profile and the dynamic balance between cliff recession and shore profile reshaping. So yeah, that would be great. But at the moment, we work with what we have. So yeah, so to come back, let's just compare what we've got, these new indicators of cliff toe sensitivity in the first column or second column there, with the modified Bruun Rule that we were looking at against the criteria I was discussing a little while ago. So basically, the new indicators tick all the boxes that the modified Bruun Rule didn't tick, except sediment budget representation where the two are reversed. SCAPE, of course, can be used to tick all the boxes if you want to go down that route. So I think what I'm trying to say with this slide is I completely recognize that the contribution that we're making here with these indicators is really broad brush, and it's very generalized, and but the idea is that the current state of the art, as it were, is not that high. It's not as though we've got these fantastic methods that the new method is trying to compete with. That what we've got is better than nothing, but it's not that great yet. So even this rather broad brush method that we're offering here, I think that probably has a place to improve our projections in certain settings. And if we think about the kinds of settings that it might be appropriate, well, that probably hangs on this question of the sediment budget, really. If you've got a site where the beach seems really deep, and it's all, we can believe that it's all, recession is controlled by the sediment budget, then yeah, perhaps a modified Bruun Rule is really the way to go. If we've got a site where the beach is quite sparse, then perhaps the shortcomings of the modified Bruun Rule are really so much that we can't really have much confidence in it. And perhaps a new method is going to provide useful insight. Of course, most sites will be somewhere on a continuum between these, so it may even be worth applying more than one method and seeing what they say, and putting some hard thinking into which is more plausible in terms of capturing the fundamental behaviours driving cliff retreat. I should say it would be useful in thinking that through if we took time sometimes to measure the depths of beaches to find out just how deep the shore platform is beneath the beach. That's not something that is normally done, but it would, I think, be valuable for this kind of problem. So coming to the end here, project outputs. There's a technical report and a user guide which have been written and are being reviewed. The data is ready for dissemination by the Channel Coastal Observatory. That around about the end of the year, probably. And our next steps in the project, there'll be a technical workshop where we'll invite people along to have a go at using this data, this method. If you're interested in attending, please let me know. And there'll also be some webinars like this to explain it perhaps in more depth. And the data will be delivered, as I say, via the Channel Coastal Observatory. So yes, thank you very much for your attention this lunchtime. If you've had any questions, we'll look at them now. I expect Anya will have compiled them as we've been going along, if any have been submitted. So I'll hand over back to you, Anya.
Yeah, I've actually only got one so far, so yeah, do feel free to submit them, but I can start with the first one we've got here. So the question is, what approach would be most appropriate for non-cohesive sand dunes or similarly very soft coastal forms? So
yeah, so if you're thinking about sand dunes, then you're very much in the realm, or the Bruun Rule was originally designed for. It's the idea of the Bruun Rule is that it picks up a sandy beach that's backed by dunes. So any erosion at the top of the profile provides sort of 100% sand or beach suitable material, which is then distributed across the profile. You get into some very interesting realms when you start thinking about rock which is consolidated and contains quite a lot of sand. So I'm thinking here places like Bournemouth, which I was working on a year or two ago. So that, looking at the cliffs there, sometimes I look at them and I think, well, what's the difference really between this cliff and a sand dune? But there was actually there was a distinct difference. The amount of beach suitable material that the cliffs were providing turned out to be surprisingly small, and there was a definite shore platform surface, so a kind of a consolidated layer on which the beach was resting, so that they did exist as two distinct phases. So actually I was surprised for the Bournemouth cliffs how appropriate the kind of the scape type conceptualization was, where you've got this kind of distinct soft rock boundary that's gradually eroded. But if it's a sand dune site, then yeah, your Bruun appears to be still your best bet.
Okay, we've got another one here. Will this research be used to update the National Coastal Erosion Risk Mapping?
I hope so. The agency still has to continue considering whether it wants to release the results. Obviously, the results are intentionally conservative, and so there are that has to be thought through. But once they're assuming that they are released, then they will be available generally to everybody, and so it would seem sensible for the next revision of NSERM to take proper account for them. Hopefully, it will make the revision a simpler task. It'll make it easier for them, and we have designed the outputs to dovetail very nicely with the method that they used in the first iteration of those maps. So we've designed it intentionally so that they can sort of pull out the module that they were previously using to deal with sea level rise and just drop this one in, and it should, only of course in places where the new method is appropriate, but it should be quite straightforward for that to happen.
Okay, another one here. Does the steepness of the profile affect the calcs, or is it all proportional?
So the steepness of the profile is, I argue, very important in regulating the cliff retreat. If your profile gets over steep, if your shore platform gets over steep, then the waves just become more vulnerable, and so they're more likely to retreat in the near future. But as they retreat at that accelerated rate in the near future, so that tends to flatten off the shore platform. And I think that dynamic balance between slope and cliff retreat is key in many places to kind of governing the overall recession. In terms of the outputs of this particular research project, that's sort of all implicitly accounted for in the simulations, so that the simulations track these changing slopes as they change spatially and through time. It's not, you can't see from the output the indicators of cliff sensitivity. You can't see, you couldn't deduce platform slope from them, but the platform slope has implicitly influenced those indicators.
Okay. Got another one here. Do you know how this work will be used to influence flood risk management plans within the EA?
So it's often the case at the coast that coastal flooding and coastal geomorphology and coastal erosion are intimately connected. And we have, I mean, some of my academic work, when I was with the Tyndall Centre for Climate Change Research, we developed the Tyndall Regional Coastal Simulator, which really demonstrated very nicely this interconnectivity between the erosion of the cliffs of Norfolk and then flooding of the Norfolk Broads. How erosion of the cliffs was a really, really good thing in terms of releasing sediment and making it less likely that coastal flooding would happen. So that interconnectivity was there in that study, and it is often there in coastal sites. And it tends to be quite a challenging problem to connect the two up. So we were able to do it in the Tyndall Centre. It's not always possible to sort of repeat that success. And there are a lot of people who've been working away at this. So I would say in terms of how this work might influence so coastal flood risk assessments, you can imagine sites. I mean, if you think of somewhere like Double Dykes near Hengistbury Head, you know, there's coastal erosion going on at a very narrow part of bit of land, a narrow but raised bit of land. Once that erosion results in a breach, so we can expect the flooding around Christchurch to be significantly affected. So these results you might use then to estimate how much more quickly that breach might happen as a result of sea level rise. I mean, I would prefer for something like that for a bespoke model to be, but if there were no funds available for that, then one might envisage using the results of this work in that sort of context.
Okay, well, I don't think we actually have any more at the moment. So I guess we can wait a couple of minutes for any more to come in. This is more a question to Barbara of Simon at the moment. If there's further questions from people, are they able to pass them on? Mike, you happy to receive questions as a result of this presentation?
Yeah, no, that's fine. If people have any queries.
Oh, we've got one more just come in. You mentioned that rebound might have been underestimated. Could you expand on that?
So, yeah, so one of the really interesting things that's come out of this work is just how important the long-term history of sea level is in determining future sensitivity to sea level rise. So this was a real insight, I think, from us. So that meant that in this phase of work became much more interested in.
Mike, I think we might have lost you there. I'm not sure if that's just
been over the last 10,000.
Sorry, I was just going to say, Mike, you cut out there. I'm not sure if that was just for me or for others as well, but I don't know if you want to maybe repeat from the beginning of your answer to that. I lost most of that there.
Oh, I'm sorry. Yeah. So, so these long-term sea level changes, it turns out, are very important, and so we were supported by the University of Sheffield, Sarah Bradley, who's run these amazing models of glacial isostatic rebound, loss of ice sheets. But there's a great deal of uncertainty in the parameters of those models, so and it's quite difficult to calibrate them. So they basically, she can provide, say, 15 different simulations of those changes, but can't necessarily tell which of those is more likely, more plausible. So we, as I say, chose a relatively conservative interpretation of that, one in which sea levels were really quite high towards the end of the Holocene. And it seems as though that has introduced too strong a bias in the north for our northern sites. But it's a relatively easy job to select a more central of those simulations of glacial isostatic adjustment. I'm not that actually answered the question, but maybe that gives you more of a sense of what we had to work with there.
Okay. Yeah, I haven't got any more at the moment. So I don't know if we want to. Oh, got a response. Thank you for that one. So that's good. Yeah, maybe we sort of end this presentation here. Yes, mention if you've got any further queries, I'm happy for you to email me or Mike. So my email is also anya.fisher@wsp.com. And yes, ready for our next presentation on Thursday, same time at 12:30. And that one, part 2, is shoreline management plan refresh before the present and into the future. So we've got 2 presenters on that one. And as I said before, unfortunately, Friday is going to have to be postponed, but I will get that rearranged so we can deliver the third part of that. So yeah, any further questions, then let us know. But thank you very much for attending, and this will be uploaded as a recording in due course. So keep an eye out for that. And thanks again to Mike for taking the time to present. That's really interesting. So thank you for that. Lovely.
Yep, thanks to everyone for taking the time out to listen. I hope it was of some interest.
Great. Right, thank you very much, everybody. Have a good rest of your day.